So we left off with this problem. We'd started out, and this was the Fourier series for a wave that looked something like this, a ramp. I think we did one where the ramp then went back up, but this one it comes down here like this, and then up like that. So a little bit different. And we had the solution that looked something like this. And we wanted to put that into the phasor domain, or get a phase spectrum on this thing. So to do that, I wanted to be in consistent trig terms, so I needed to either convert them both to sine or both to cosine, or probably a little more comfortable with cosine. So we converted them to cosine. And then we converted from the time domain, which was this expression here, to the phasor domain, like we've done many times. Certainly last term we spent a lot of time doing that when we were doing AC analysis. And then I said if n was equal to 1, we evaluated this and came up with this value. Then n is equal to 3 and 5, because we were looking at the odd terms there. So that's where we left off last time. And I wanted to continue to work with this. If I were to go back and to put this into a time domain, so going back to the time domain, we could see that the voltage in the time domain would be 7.5 times the cosine of what? We started out with n times, n times, well, we would have 1, because this is going to be the first one, so it would be 1 times omega naught times t. So I have omega naught t minus 122. And then I'm going to add to that 2.2 times the cosine of, now n is equal to 3, so I'm going to have 3 omega naught t minus 102, and I will add to that, get that right? Yeah, 3 omega naught t. This would be, of course, 1 omega naught t, and add to that for the fifth 1.3 cosine of, we're doing 5 omega naught t minus 97, and we could continue on with that. So we can make go the full thing there. Now the reason for doing this is eventually I'm going to put a circuit up here, and we'll look at putting these values through the circuit. One of the things we're going to do with the circuit is we'll talk about omega being equal to, or omega naught being equal to 2. So if I take this expression here, and I guess kind of oddly writing back up the paper, but with omega naught being equal to 2, what do I have? I have then 7.5 times the cosine of 2t minus 122. 122, I get an extra 2 in there, don't I? There we go. And then I'm going to add to that 2.2 times the cosine of 3 omega naught, so I'll have 6t minus 102. Sure I'm getting that right, yeah. And then the last term, 1.3, the last term we're doing, times 10 cosine 10t minus 97, and continue on. So with that, what I'd like to do is introduce that function to a circuit, and I think I alluded to this as we were finishing up last time. So if my circuit looks like this, I'm going to take my voltage, I think we're talking about V of t, and I'm going to introduce it there, and I'll have a resistor and a capacitor. We make this a little more challenging transfer function than we've seen in the past. And we'll talk about V naught t. So I'm going to look for that. I'll say that this is 1 ohm to keep the numbers easy. We'll say this is also 1 ohm. We'll say this is 1 farad. That's kind of weird, but keeps the numbers easy. And 2 ohms on that one. Okay. So I'm going to put my wave that I have into there. So essentially I'm going to do it by putting this. This is going to be my input. I'll put those into this transfer function and see what I get on the output then. So remember we said we were going to take omega naught being equal to 2. So if I go through this thing, I guess the first thing I could probably do is just come up with, I guess maybe we could talk about the current here. If I talk about the current I just need to, I is going to be equal to what? The voltage, V. So if I change this in phasor form, I could say that that's V. And then I have to divide by the total impedance. And I have a parallel branch here that's going to be what? Product over sum. So let's see, this parallel branch I have 2 ohms there. And let's see, so this one, this branch turns out to be 2 ohms. And what does this branch turn out to be? Minus J, I guess maybe I'll just say it's 1 over J omega C, right? Which C is 1. So with C being equal to 1, I could just say it was 1 over J omega. So when I deal with that, I'm going to have this product, which would be 2 divided by J omega, multiplying this 2 here by this J omega, product over sum. And then I'm going to have 2 plus the 1 over J omega. And then I have to add that back to that 2 up there. Okay. So I have something that looks like that. So probably when you're faced with something like that, getting a common denominator is probably the best plan. So what does this look like in terms of a common denominator? I could say that that was multiply both sides by the denominator, so I'm going to have 4 plus 2 over J omega, and then add it to that 2 over J omega up there, and I get then everything over this common denominator of 2 over, or 2 plus 1 over J omega. So let's see, this turns out to be 4 plus 4 over J omega divided by 2 plus 1 over J omega. So we'll multiply by 1. I'm going to multiply by a weird one, J omega over J omega, which should give me, what, 4? Yeah, 4 plus 4 J omega. I switched the terms there because I always like the complex term second. And then this is going to be 1 plus 2 J omega, again switching order of the terms. Okay, so that was what was there. So I could say then that I is really equal to V times this. So because this whole thing's in the denominator, I'm going to flip it. So I have then the denominator here times V, 1 plus 2 J omega, and then this term will remain in the denominator, 4 plus 4 J omega, right? So far so good? Okay, so that's the current there, and maybe we want to come up with the current here. Maybe I'll define this as I1. So I can say that I1, so track of where I'm going. So I1 is going to be that current I times what? I have to use current division, don't I? So I multiply by this impedance, which is 1 over J omega, and divide by the sum of the two impedances, which is 2 plus 1 over J omega, current division. Yeah, eventually I'm figuring that if I get to this one, if I get I1, I just multiply it by 1 ohms. Yeah. Okay. So let's see. I need to put I in here, so I have a so I could say that I1 is then equal to I. So I'll have to put that in here. Does that make? Yeah, we can probably do that. So I'm going to have V and maybe I'll hold off a little bit. I can probably clean that up, right? Yeah, now you're thinking. So multiply top and bottom by j omega. So we would have then I would be just alone in the numerator, wouldn't it? And we would then have 1 plus j or j2 omega. Okay. So now I'll make my substitution for I. And I don't know that we need to do that first. It's probably a little easier. So I1 is then V times 1 plus 2j omega divided by 4 plus 4j omega, and then I have to multiply this thing by what? 1 plus, yeah, I'll write it 2j omega, I guess, to be consistent how I've done it. Okay. No, we lucked out there. Isn't this the same as that? So I get to cancel that out. So I've got down that I1 is V divided by 4 plus 4j omega. We go back to the circuit. We've got I1 pretty well defined, so we would know that V naught is just 1 times I1, isn't it? So V naught in phasor form is 1 times I1. So I would have V divided by 4 plus 4j omega. Yeah, I think that's okay. We're still in phasor form. So yeah. Now before we go back and start to put the values into this thing, I think I probably need to, this is omega, so I think I will change this to n omega naught. Okay? So when I do that, we come up with V naught being equal to V, our input voltage, that's what's going in, isn't it? That's what's going in, divided by 4 plus 4j n omega naught, right? Because it's going to change with n as the frequency increases. We have to have some way for accounting for that, so we've changed this omega to n omega naught. And then remember that omega naught was equal to 2. So when I change this to 2, I could say that I have V divided by 4 plus 8 jn, right? Maybe I better put the j out in front and say that it's 8n. Okay. Troubles with that? Everyone's good so far? So this is the one that I want to use. So I'm going to take that and I'm going to start to put these into it. Let's see how that works. So the first one is 7.5 at minus 122. So I'll take, so this is n equals 1. I have 7.5 at minus 122, and then I'm dividing that, because I've got the function here, I need to divide it by what? 4 plus j 8n. So I have 4 plus j 8, because n is equal to 1. I don't need to worry about the n value there. So when I get done with that, I'm just going to do that. I mean, if I could do this by hand, I would convert this rectangular form to a polar form, divide the magnitudes, and subtract the angles. Probably easier just to go to my calculator and put those two numbers in. And when you do that, let's see what we come up with. So I come up with 0.84 at an angle of 175. So that's what I'm getting up for my output. So let's try n is equal to 2. What did we have for the input when n was equal to 2? We had this, no, not n equals 2, sorry, n equals 3. When n is equal to 3, I had 22.2 at minus 102. So I will do 2.2 at minus 102. And then in the denominator, and I'm just going back to this last page, I got 4 plus j8n. So 4 plus j, 8 times 3, right? 8 times 3, which is, of course, 24. So when you run through that, what do we come up with? .090 at an angle of positive 177. Okay, and I guess we've got it. I'll do it one more time. When n is equal to 5, going back to our work from last time, 1.3 at minus 97. So 1.3 at minus 97. I'm dividing by 4 plus j. I'm multiplying 8 times 5, right? 40. .032 at an angle of 179. So we're getting a little phase shift. The values are getting quite a bit smaller. But these would then be this is the phase spectrum for the output. Or going back and looking at the circuit, that's the voltage across that resistor there. Well, we could put this back into the time domain if we wanted to. So we could look at V0. That's the voltage across that 1 ohm resistor there that I was just showing you. We could say a 0.84 times the cosine of, this would be what? Omega n, omega naught t, so I'll just have 2 times 1, which is 2t, and then minus 185.4. No, that's the complement of that, isn't it? So I'll just say positive 175. So positive 175. Okay. And then the next term is going to be positive 0.090 times the cosine of, what do we have? N omega naught. So we have 3 times 2, so 6t plus 177. Plus, and I can do the last one, 0.032 cosine of what am I going to have there? N is equal to n omega naught, so I have 2 and 5, so 10, right? And we could keep going if we wanted to. So just a little different way to work out a problem. If you were to plot this, then you would see what the output of this thing was. We took this wave here, like that, and we put it through that circuit. So this went into there, and this is what we get for our output. Okay, and I actually did that. I plotted that out. So if you go to the website, and this is the Fourier demo number 5. So this is under the Fourier series folder. And let's see, I just used a MATLAB program. You can see the loops here. I have a loop for time. So that's taking me through. I mean, if I look at this on the input wave, I'm just slicing it up like this as I loop through time. And then I loop through n. Okay, how many n's am I going to have? And it looks like I put the n max, n is going to be equal to 100. So let's see what that looks like. Let's just the rest of that, just so we get it documented there. Here's the output. This is what we're looking for. So this is the input signal. So that's that wave that we've been looking at, the one that looks like that, which is not bad with n is equal to 100, right? N is equal to 100 looks pretty good. I mean, you got a little there, but that's not too bad. And then remember our amplitude here apparently was 10, and our output is coming up quite a bit lower and has an interesting shape. So it looks like more of a triangular wave. So there's the input and there's the output. Well, I'm still always intrigued on this thing with how good the Fourier series is for lower values of n. So what I did then was I just took the same program, and instead of having my loop go from, well, not very good programming technique, I still left n max equal to 100, but it doesn't do anything because I set n equal to 1, 3, 5, and 7. So you'll see this as demo number 4 in the folder. So I've only got the first 4, right? At 1, 3, 5, and 7. So let's see what that looks like. So it's not too bad. Okay. Now if you're really pushed, you could do this by hand. So n equals 1, 3, 5, and 7, period. No more. So it's not bad. I think we'd have a pretty good idea. We got the same results. So again, you don't have to go very far towards infinity to get a pretty good approximation. So you can see those on the website. They're in MATLAB. Let's look at the code here. You should be able to do them pretty well in FreeMat. So if you're running FreeMat, they should download pretty well. Well, I wanted to, are there any questions of that problem? You okay with that? So I wanted to do a couple more examples. This example, I wanted to try and put this in a context. I mean, what are you going to do with this? I mean, you recognize that, where'd my little drawing go here? We have this circuit. We put something into a circuit and we get an output. Let me put that into a better context. Why would we want to do that? So I want to talk about maybe building a power supply. So we come from a plug-in. These are kind of long prongs, but that way you can plug it in from across the room. And probably the first thing we want to do is we want to go through a transformer, right? A lot of coils here, and we'll drop it down. So we'll have only a few coils there. So this will probably be about 120 volts, and maybe we get this so it's about 12 volts. Now this is AC in, this is going to be AC out, right? Just like that transformer I brought in when I was showing you that little demo with the oscilloscope and the dimmer. We're still getting AC out. And if I want to turn this into DC, so I'm trying to make a power supply or something like that, I could go with a this input. We'll take a sine wave. I could go with a half rectified wave, and I mean when I get to this point, all I have is a smaller amplitude, right? It's still sinusoidal. And what I could do next, if I could go with one diode and I would get a half rectified, it would look something like this. Okay, that's going to be harder to make a nice DC signal out of. So what I propose is we go with a full rectified wave, and then we'll get something like that. So to go with a full rectified wave, I need 4 diodes rather than just one. If I just put one diode in, that'd be half rectified. So let me put my diodes in here. And you'll talk a lot more about diodes and what happens with them next year. So, and basically with a diode, current can only go one way through a diode. So I'm going to take this as the plus, the minus. So I'll bring my AC into these 2 points, and then at this point here, I come out and I will have my minus. Okay. So probably what I have at this point is going to start to look something, well, is going to look something like this. That's fully rectified. But that's still a long ways from DC, right? So what we'll do is maybe we put a little resistor on this, and maybe we'll put a couple capacitors in here. And hopefully when I get to this point, at this point, I'll have something that looks like this. So maybe have a little variation up there. That'll be something that I can start to use really as DC at that point. Okay. Well, what the capacitor is going to do is it's going to collect over these low points and discharge at the high points. Okay, so that'll smooth it out. And a lot of power supplies have big capacitors. Okay, so let's see what we got going here. I think if you go to a handbook value and you take a fully rectified wave, that'll probably look something like this: 2 times the amplitude divided by pi plus the sum n equals 1 to infinity of 4a divided by pi times 1 minus 4n squared times the cosine of n omega naught t. So the Fourier series looks something like that. Let me double check that. Yeah. Okay. So that's what the Fourier series looks like for the fully rectified wave. And then we really have kind of a circuit here. So if I come down and look at that as a resistance and a capacitance, I could combine those 2 capacitors. A lot of times we put multiple capacitors in parallel like that, because that would increase the values, right? If I put resistors in parallel, it decreases the values. When I put capacitors in parallel, it increases the value, right? Yeah. you've ever done any MIG welding or whatnot, a good MIG welder, the whole bottom of it's basically capacitors, trying to smooth that out, AC that's coming in. So we've got R 1 over J omega C. This is our in, this is our out. Okay? So we're going to put this into this, and we're trying to see what we come out with. But we're going to have to come up with a transfer function. So your transfer function, V out, would be equal to V in times 1 over J omega C divided by R plus 1 over J omega C. Classic voltage division, right? I'm going to multiply by J omega C over J omega C. And this turns out then to be V in divided by 1 plus J omega RC. Can you go through that? Yeah. So we could then put this into magnitude angle form. We could say you'd put whatever you get for your input voltage, and magnitude in the top is 1, so I don't need to worry about that. Magnitude in the bottom is going to be what? 1 plus N omega naught RC squared. So I changed out this omega here for N omega naught. So I've got N omega naught times RC squared. And then that's going to have an angle. So I'll just put the angle up there. Let's see. It's in the denominator, so it'll be a negative angle, because there's whatever angle we have on Vn, we would have to subtract this angle. It'll be minus the arc tangent. We did a lot of this last time. Of N omega naught RC divided by 1, right? So I can put my wave into this thing, and I should get then the output. So when I go through that, I'm not going to go through the numbers. You can play around with that. But this is what you get. So we said that our input at this point, I'm not worrying about the transformer. We did the transformer last term. So I'm going to start at this right here. So that's my AC input. And then we take this AC, and I just, instead of coming down here, I flip this piece up here because it's fully rectified. So this is the in, and here's the out. Okay, that's what I'm getting out of this filter. So there's our in, and there's our out. And you might say, well, you're not, that's not looking too good, because I take a fully rectified wave and you're getting basically a sine signal out. Well, remember, you have to look at this. We've got an amplitude here of what, 12 volts, right? What's this? About 0.2, 2/10, right? Okay. So when I said that what we're getting out of this probably has a little ripple, that's what we have here, right? When I look at it in context, when I take these two graphs, if I take the input wave, that's the sine wave that's coming out of the transformer. Okay. And then I use the 4 diodes there, the diode bridge, the rectifier, and I flip that one up. That's what we started with right there. And then this is our output, which is pretty good. I mean, when you look at it in the same scale, these go away, right? You get something that's pretty smooth. So that wouldn't be a bad power supply for us. Yes? The tangent, remember, it's always the complex portion in the numerator with the real portion in the denominator. So it's N omega naught RC. So you could mess around with this a lot. I mean, if we haven't talked about putting any load on this, if you want to put a load on there, you might see what happens. Does this thing fall apart? It shouldn't fall apart. But if we put a load on it, what happens? So I didn't go through this in as much detail as we've done in some of the past. That's not the purpose of this. Hopefully the purpose of this was to show you that there's real use for this. If you get into designing power supplies or something like that, this is a nice way and a reasonable way to model those. Questions with that? Well, the last thing that I wanted to do, I've got one more problem here. I'm just going to look at one of the homework problems. Hopefully you've been going through the homework problems. So the problem would be B5. So I'm going to go through and tackle that problem, just make sure we're comfortable with that. As far as the midterm goes, what kind of problems could you expect? All of the B section, none of the C will be on the midterm, but all of the B section will be on the midterm, so B5 is a timely problem to do. And all of the A section. So we're going to have Bode plots and we're going to have Fourier work on there, so it's all of the A section and all of the B section. And as you'll see, I fit B5 onto one page in the solutions, but that may be a little deceiving. So if you're thinking, oh, there's only 5 pages of homework problems or something like that, be careful, because I kind of abbreviated a lot of this. So let's go ahead and go through B5. Our first task on B5 is to parameterize this wave. Should be kind of interesting. And incidentally, this will be our last problem in Fourier work. When we get together next time, we'll go into Laplace transform, which will not be on the exam, but we'll get started on that, and that's how we'll finish up then the term. Okay, so I'm going to say this goes from positive 10 to negative 10. We'll say it's a voltage wave. And there's pi. Here's 2 pi. Time in seconds. So the first thing I'm going to do is parameterize this wave, and then I'm going to put it into a circuit. So let's see. If I look at the wave, what kind of symmetry does it have? Odd. Yeah, definitely odd. Then if I look at the, so if I take this as one period, do I have half-wave symmetry? Yeah. If you flip it around the half-wave, it doesn't land on itself. How about quarter wave? Flip it around the quarter point, does it land on itself? No. So I would say odd for sure. Be a little more complete here. No, half, and quarter. Okay? So odd, but odd is not bad, because what do we get out of odd? The average value is equal to 0, and a sub n or a sub k is equal to 0. And we can then come up with b sub n. That's going to be equal to what? 4 divided by the period t times the integral from 0 to t over 2 of the function times the sine of n omega naught t dt. I've done these in terms of n. That's fine rather than k. Well, this is nice. I only have to go over half the period, right? There's half the period. That's pretty easy. So what's f of t? Going to have a rise of 10 over a run of pi times t, right? And while we're here, t is equal to 2 pi, so omega naught would be 2 pi divided by t, which gives me what? 1, right? So if I put this up in here, I can say that b sub n is equal to 4 over t times the integral from 0 to t over 2 of the function, which will be 10t over pi, times the sine of n omega naught, that's just 1. So I've got n times t dt, right? So we look for the form. What kind of form are we looking for here? The integral of x times the sine of ax dx. Okay. We've done that one lots of times before, haven't we? Yeah. Because you'd end up with this b sub n being 40 divided by t times pi from 0. Let's see, if t is pi over 2, this is going to go to pi, isn't it? Of t times the sine of n t dt. So we saw that a lot before. I'm not going to belabor that. I'll just jump to what this turns out to be equal to. We have minus 20 over n pi times the cosine of n pi. Okay. So there's some work in here. And however you want to do it, it's a good opportunity for you to do some practicing, whether you want to go with a computer algebra system or look it up in a table. That's up to you. Probably a good thing to figure out for the exam. Then I think if you're following along in the homework solution, I play the math game here and say that we have minus 1 taken to minus 1 taken to the n plus 1 times 20 over n pi. Okay. So am I looking at the odd function? Am I looking at b sub n is just for the odd terms, isn't it? Yeah. For n equal 1, or is it all terms? Anyone got that in their notes? Yeah, is this n value in here for just the odds, or is it for all terms? I think it's for all terms, isn't it? It's for all terms. Yeah. Okay, so 1, 2, 3, and so on. So if I look at this, when n is equal to, looking at the unit circle here, when n is equal to 1, I have the cosine of pi. So I'm going to be over there at minus 1. So when n is equal to 1, this turns out to be minus 1, and I'm left with 20 over n pi. What happens when n is equal to 1 here? I square that, so I become positive. Yeah, I get the same value. When n is equal to 2, I get over here as a positive 1, so I'll have minus 20 over n pi. When n is equal to 2 here, that's cubed, so yeah. So that works. Thinking about the exam, I would not get panicked at all about this. I'll be perfectly happy to accept an answer like that. So now we need to put this into the function, right? We have 0 average value, a sub n is equal to 0, so all I have to worry about is b sub n. So I could say that the voltage is equal to the sum. We said the n values are 1, 2, 3, and so on up to infinity of b sub n, which we've used this. I'll just go ahead and continue with that. Minus 1 taken to the n plus 1 times 20 over n pi. And b is in front of the what? The sine term. So I have sine of n omega naught. So just n times 1. So I'll say nt. Good with that so far? Now we could probably work the problem with sine, but we've done most of our work with cosine and all of our phasor work, so maybe that's probably the safer thing. So I'll switch this 1, 2, 3, and so on up to infinity of minus 1 taken to the n plus 1. And I'll have 20 over n pi, and I'll do the cosine of nt, and what do I have to do? Minus 90 degrees. Good. Okay. So that's our input. That's our input. So let's look at the circuit. So we said we're going to be putting in to this voltage source here. We got a 2 Henry inductor. That's a good sized inductor. Two ohm resistor. And what we'd like to do is I would like to come up with the expression for this. I think in the homework problem it's I naught of t. So I'd like to figure out what that is. So we're putting the value that we just found. This is our input. We're putting that in there, and we're trying to come up with that I. So if I write this in as some phasor voltage V, and I write this I as I naught in some phasor form, let's see if we can get that. We could talk about a voltage across here. We'll say this is Vx. So I could say then that Vx by voltage division is equal to V times what? The impedance here. What's the impedance for this branch? Product over sum. So 2 times J 2 omega. Divided by the sum, which is 2 plus J 2 omega. And I think what I did then at that point is I said I'm going to say that omega is equal to n times omega naught. And what did we say that omega naught was? That was 1. Shouldn't look like 7. That was 1. So everywhere that I have an omega, I'm going to replace that with what? An n. Okay. Normally I'd replace it with n omega naught, but because omega naught's equal to 1, I'll just replace it with n. So now this thing would look like what? 2 times J2n divided by 2 plus J2n. Okay. So that's that. I can put that in there. 2 times J2n divided by 2 plus J2n. And then I have to divide by the sum of the whole thing, which would be what? This 1 ohm plus then what we have in the numerator. Something like that. Yeah, this could be work, couldn't it? Yeah. What do we have to do? Common denominator? So I'll have 4J4N divided by 2 plus j2n all over 2 plus j2n plus j4n all divided by 2 plus j2n. Denominator of a denominator is a numerator, so I get to cancel those two, and we come up with v times j4n divided by 2 plus j6n. You done that right? So what's I naught? I naught should be equal to, if this is Vx here, we know from very early on that that's also Vx there. So I can just take Vx and divide it by 2 ohms, right? So I have then 1/2. I've got Vx, so I'll multiply this V times J4n divided by 2 plus J6n, and we come up then with I naught being equal to V, the input voltage, times J2n divided by 2 plus J6n. And I think I took the, I guess one thing to repeat in here, I don't think I showed all this algebra in the homework solution. So like I said, there's, I was kind of terse as I went through there. So make sure you allow enough time as you work through these problems. I think I took this one step further and said that this was equal to V times, let's say I have a 2 in there, a 2 in there, and I can factor a 2 out of there. So I have essentially this term Jn divided by 1 plus j2n. No, 2 comes out, so 3n. Yeah. So I think what I'll do, so we're going to put this is where we put our input. That was back on this page here, so we're going to take that and we're going to put it into there. So maybe I'll write this piece in magnitude angle form. So what's that going to look like? What's the magnitude of the numerator? Should be n, shouldn't it? Divided by the magnitude of the denominator, 1 squared plus 3 squared n squared. So I'll just say 9n squared. And it's going to have an angle of what? The angle of the numerator, it's because it has a j, that's 90 degrees, right? And then I have to subtract, because it's in the denominator, the angle of the denominator. What's that going to be? 3n over 1. Everyone's okay with that? Okay. Angle of the numerator, 90, because it's j. Angle of the denominator, just the imaginary portion, arctangent of the imaginary portion over the real portion. So let's put that all together. So I'm going to take these and see if I can put them together. So that's what's going in, and this is what it's going into. So I can say that my I naught in the time domain, because this is in the time domain, is going to be equal to, I need to take this thing and multiply by that thing, right? So I'll have sum 1, 2, 3, and so on to infinity of minus 1 taken to the n plus 1. And then I have the 20 over n pi. And then I'm modifying the magnitude by this, so I better put that in there. N divided by the square root of 1 plus 9. That was the 3 squared. And n squared. And then I have the cosine function. So I have the cosine of nt. And then I have to, subtract 90. That's from right there. I'm done with that piece. And then I've got this. I need to modify this angle. I'm going to add 90 and subtract the arctangent of 3n over 1. I'll just write that as 3n. Okay. So I should be able to tidy that up a little bit. Now we'd say still have this. N plus 1. And let's see, I can cancel those n's, and I have 20 divided by pi times the square root of 1 plus 9n squared times the cosine of nt. My 90s cancel. I have minus then the arctangent of 3n. Okay. There's amps. And that's my output. If I wanted to tidy it up a little bit more, I guess I could bring the 20 and the pi outside. I don't know that that would make it any better. I think I'll just leave it like that. So again, another problem where we take a circuit. We have to come up with what the input looks like, then we run it through the transfer function of the circuit and come up with the output. So I've done that many times, and I just wanted to do this homework problem so we'd get one more good problem to look at, and also show you that the homework, I kind of abbreviated those solutions so they didn't have to go on for so many pages. So some of this work that I did here in the transfer function I left off, some of the work that I did in the integration here I left off. So don't look at the homework and go, oh, it's only 8 pages. I can do that, in a couple hours. It's probably a little longer than that. So be careful as you're starting to prepare for the exam. Questions then? I guess that gets us to a good stopping point.